Hello, this is Clint Halstead, and this is an internet course called Introduction to Microprocessors. Today we're going to be studying chapter 3.6, 3.5, 3.6, and 3.7 of the book entitled Designing Embedded Systems with PIC Microcontrollers, Principles and Applications by Tim Wilmshurst. Okay, so today we're going to talk about the oscillator and the power supply. So the choice of microcontroller clock source determines some of its fundamental operating characteristics. While faster is better in terms of operating speed and programming execution, faster is definitely worse in terms of power consumption. So we need to keep that in mind when we're designing our microcontroller project. All the timed elements within the microcontroller almost invariably depend on the clock characteristics. If stable and accurate timing is required, then the clock oscillator must be stable and accurate. The clock source must therefore be chosen with care. So let's look at two common oscillator circuits. The first oscillator circuit here is an RC oscillator, and we talked a little bit about Schmitt triggers. This is a Schmitt trigger that we're going to use, and we're going to connect from the output. We're going to connect a MOSFET switch. It's going to pull down on its input, and then we're also going to have an R and a C. Now, so what's going to happen here is that the supply voltage, let's assume it's at 5 volts, it's going to charge through the electrons, or current's going to flow through the resistor and start to charge the capacitor. The capacitor voltage is going to start to rise slowly. It's going to have an RC time constant. Okay, the Schmitt trigger is going to have an upper threshold and a lower threshold. Okay, so in order to, once it meets the upper threshold, it's going to want to tend to charge to all the way up to 5 volts here. But at a certain level, the upper Schmitt trigger threshold is going to be met, and in that case, the output is going to switch high at that point. So at this point, the output will go high, like this. Okay, so when the output goes high, actually it's going to turn on, this is going to go to 5 volts, so it's going to turn on this switch, which is going to quickly discharge the output. Okay, so the output is going to quickly discharge, the input is going to discharge. Sorry about that. So the input is going to start to discharge. So at this point, the threshold is reached, and then the input is going to start to discharge. Now when the lower limit of the Schmitt trigger is met, and then the output is going to go low. So at this point, the output is going to go low. So here the output is going to go low quickly, and then the cycle is going to repeat again. So basically, you're going to have this Schmitt trigger level like this, where the output is going to charge an RC time constant like this. That's the initial charge, and then it's going to fall until you hit this level. Okay, and then it's going to charge again at an RC time constant, and then it's going to be discharged again by the MOS. So this period of time here is the MOSFET discharge cycle. So this is the MOS. A-M-O-S. MOSFET. So if we recall, this is the MOS. And then this period of time is the RC time constant, controlled by this R and this C. Okay? And then this again is the MOS discharge time. So you're going to have a rise time, which is an RC rise time, and then a MOS discharge time. So RC rise time, MOSFET discharge, RC rise time, MOSFET discharge. So the cycle is going to repeat over and over again, and it's all based on the threshold for the Schmitt trigger. This is the threshold high, and then this is the threshold for the low side. Okay. Now let's look at the quartz crystal. The quartz crystal oscillator is a little bit different. Here we're going to have an inverter, and we're going to have connected a crystal. Now the crystal at a certain point on the crystal oscillator, it's going to have sorry, it looks something like that. That's kind of the transfer function of a crystal. At some point, the crystal is going to pass current, but it's going to be 180 degrees out of phase. Okay, 180 degrees out of phase, and this is going to be called the series resonant point. Okay, so at the series resonant point, it's going to pass current. That's going to be here in the middle, so it's going to be zero impedance. So if this is the impedance of the crystal, then at some point called the series resonant frequency, then it's going to pass current, but it's going to be 180 degrees. So it's basically going to essentially be two inverters, okay, 180 degrees out of phase. It's going to pass that voltage. So it's basically going to be an inverter that's going to, once it rises, then it's going to have a delay, and then it's going to fall, and then that cycle is going to repeat over and over again. It's going to rise and then fall. So 180 degrees out of phase, and then that's going to give you your unstable characteristic, where it's going to be trying to force the output opposite of the input. So, and then you're going to have feedback, so that's going to cause it to always it's never going to have a stable state. So, for example, let's say this is a 1, the output's going to try to go to a 0, but then there's going to be a delay here. Okay, so this is a delay, and then so this 0 is going to be delayed, and then it's going to try to force this to a 0. Okay, now this 0 is going to pass through again with a delay, which is going to try to create a 1. This one's going to feed back here with a delay to another 1, which is going to try to force this again to a 1, and then the cycle is just going to keep repeating over and over again. Okay, so at that point would actually occur in this case at a 0 degrees, not 180, 0 degrees phase margin point. So that's the point at which this oscillator is going to be oscillating. So let's look at the different oscillator modes for the oscillator. The 16F84A can be configured to operate in 4 different oscillator modes. We got the XT, we got the HS, the LP, and the RC. So the XT, the HS, and the LP are all 3 of those are crystal modes, and then we have one RC mode. Now the crystal modes, again, like we've talked about before, are very stable because they're dependent upon the cut of the crystal. You basically have the piezoelectric effect, which says that a crystal, if you put a voltage across the crystal, then it's going to deflect mechanically. But then if you have, and then the corollary of that is if you deflect a crystal, there's going to be a voltage across that. It's going to be made by just simply physically deforming it. And so what happens actually is that once you put a voltage across it, it starts to vibrate, and then it tends to keep vibrating if you put a voltage across it to reinforce that. So you wind up with this sustained oscillation. But what you need is a amplifier or something across it to keep the voltage always present. So we have these 3 different crystal modes and one RC mode. Now these are set with the configuration word. That's the key point here, is use the configuration word, which is going to be part of MPLab. MPLab is going to be able to download through the PIC16 the configuration word. It's just a series of 1s and 0s, really. It's going to have information in it about the crystal speed. Okay, so you got this really, really long word that the PIC kit is going to be able to send across to your chip. So we have just the standard XT, which is for the ranges of 1 MHz to 4 MHz. Then we got the high-speed mode, which is for 4 MHz or greater. And then we have the low-power mode. And keep in mind that the higher speed, the more current. So in one of these modes, you may have, for example, you may have a lot of current possibly, I think actually for the high speed mode you may have 20 milliamps on the data sheet, whereas for the one of the lower RC modes you may have maybe 10 milliamps. Okay, so it really makes a big. And now for the low power mode, you could have as little as 1 milliamp, and for the low power part, the LS part, you can even have in the microamps range. Okay, in the microamps range. That's for the LS part, like the 16 LS84, which is it's the low power part. The low speed. So all three of these crystal oscillators are set. You have to have a crystal oscillator circuit, okay? Which is, you have to have a crystal and 2 capacitors, or you have to have a ceramic oscillator. So you can buy a ceramic oscillator that has basically these three pieces already inside of it, or you have to buy the crystal with 2 capacitors. Okay, and there's 2 pins that you put on the chip. It's pin 15 and 16, I believe, 16 and 15. So you have to find these 2 pins on the part and make sure you have the oscillator there. Or you can also just simply use an R and a C in one of the oscillator pins, Osc&Pwr, I think. And we'll talk about that a little bit later. Okay, so those are the 4 different oscillator modes. Now we'll talk about a little bit how to set those up. So if you look at the chip, the actual chip, you have these 2 pins called Osc1, Osc2. Now we're talking about how to actually configure those mechanically with the hardware. So to do the crystal, then you need to have Osc1 and Osc2. So in this case, Osc1 is going to be 10, 11, 12, 13, 14, 15, 16. So this will be pin 16. This will be pin 15. So on pin 16 and 15, you actually need to connect a crystal and then 2 capacitors and then a ground. And that'll set it up for HS, XT, or LP mode. Now, if you don't want to do that, the crystals are a little bit expensive sometimes, depending. Capacitors are fairly cheap, but you still have to have these 3 components on your board. If you want to have a cheaper option, something a little bit less stable as far as having a fixed frequency, this is a very stable fixed frequency. Not going to have to worry about this one, as long as you keep your these wires short. Now, that is something to be considered. Now, when you're designing this, you're going to want to have your crystal oscillator here, your capacitors here, and then route directly to your board, okay? From your chip to your board. Make these connections short. You don't want to have your crystal way over here and your capacitors here, and then have long wires leading all the way to here. That's going to change the resonating frequency of this. This is going to have a bunch of inductance in series. Mainly, it's going to be due to inductance. So you're going to have this inductance. That inductance is going to mess up with the resonant frequency of the crystal, and it's going to shift that frequency. Okay, so you don't want to have these long wires. These long wires have magnetic fields around them that causes an inductor. Okay, and then this is an L. So anytime you have a loop, a wire loop, the inductance is going to be proportional to the area of this loop. Okay, the area of that loop. The area inside of that loop is going to be proportional to your inductance value. Okay, so if you want to eliminate that area, you could twist these wires together. Okay, so if you twist those wires together, okay, assuming that this is your filter, this is your crystal, and then this is your chip, you could twist those wires together. That would eliminate a lot of that inductance. So that would probably work if you have a situation where you're using a solderless breadboard or something where you're wiring to a crystal. So that's the best scenario there. Now, if you want to use the RC mode for the crystal, then you're going to need to have a resistor and an external resistor and an external capacitor connected to your oscillator. So you can do that by, I'll show you a picture of that here in a minute. I'll show an actual circuit using that method. And you can pick the resistor off of the data sheet. You choose the capacitor from the data sheet, and then you pick a resistor. The data sheet is going to show you basically a diagram, with some curves on different resistor values. This will be the 10K, for example. If you look at the data sheet, you pick the voltage you need, say 3 volts, then you allow these two to match up, and you can see over here it's going to tell you what the frequency is, 800 hertz, for example. Okay. And in this case, you don't need the oscillator. So this is oscillator 1 is pin 16. Okay. And in this case, pin 15, you don't really need it. So you only need the one pin, the pin 16. And also the third option would be externally supplied clock. So if you had a clock already on your board from some other clock generator, maybe a 555 timer or something, and you're trying to synchronize 2 clocks, then a good option would be to simply maybe buffer your clock with an inverter. Doesn't really matter. And then usually you want to separate the 2 clocks, as long as you don't have too much of a delay between the 2 clocks. Then you could just simply supply a clock onto oscillator 1. And then again, you're going to have to configure all these things with the configuration word. So the way you tell the chip what you want is with the configuration word, and then you set the hardware externally. You can't just set it however you want it and then turn on the chip. It's not going to work. You have to set the configuration word for it in order for it to work. So here's an example. Let's say that we have a LS part, a 3-volt part, and we're going to use a 10K resistor. And if you match these up, okay, that gives you this point. You move across, and that says 800 kilohertz. Okay. So if you had a 5-volt part and you used a 5.1K resistor, then your frequency is going to be, you read across here, it's going to be about 1 megahertz. Okay, so this is 1,000 kilohertz gives you 1 meg, so it's 1 megahertz. Okay, so that's how you do it. And this chart is on the data sheet. So this is the 16F84A data sheet for the oscillator configuration. Let's talk a little bit about the supply voltage. In order for the chip to work, obviously you're going to have to supply voltage to it. Now the voltage supply is called VDD and VSS. VSS is your ground. Okay, your ground connection looks like this, or sometimes they draw it like this: signal ground, analog signal ground. So this is where your ground connection is going to need to go to. Okay, your supply looks like this typically. It'll say VDD or 5 volts, something like that, or sometimes it looks like this. Looks like a battery symbol. Okay, so this is where you're, and then sometimes of course you want to have a switch here. You may want to put a switch there for supply voltage. Also, the PIC kit itself, if you look at the PIC kit 3, it can actually supply the voltage and the VSS as well. So this is a lot of the configurations. You're just going to use the PIC kit. PIC kit. PIC kit 2 or PIC kit 3. And it's going to have the pins here for supply, ground. It's going to have something for master clear, and then it's going to have programming data. It's going to have programming clock and programming data. Okay, so that's kind of how you do the PIC kit. And the PIC kit will supply power, but the PIC kit is going to monitor to see if you have power supplied already. If you do, it's not going to supply power. So really, inside of it has an internal power supply. And if it detects that you have power already connected, then it's not going to supply power. If it detects that you don't have power here, then it is going to supply power. So really, inside the PIC kit, there's a circuit that looks something like this with a switch, and then it has an internal supply, and it detects this line to see if there's voltage. If there's not, then it's going to connect the switch, and it's going to supply the 5 volts you need. So this is the PIC kit. That's the way it works, and it does that through the software interface. Okay. Now, need for decoupling. Okay, let's talk about this for a minute. Also, what we need for the supply, of course, we need to supply voltage either from the PIC kit itself, or we're going to supply it with a battery. You know, this could be two AAA batteries, two AA batteries. If you have an LS part, then you could use two AAA batteries, because a battery is typically 1.5. So if you got two of them, that's 3 volts. If you have two batteries, that's 3 volts. It's 1.5 times 2. And then if you have 3 batteries, then that's going to be 4.5. So that would be sufficient in most cases, except in the HS mode. Now remember, the HS mode, well, your HS mode, yeah, it should be sufficient even in the HS mode, because the HS mode is the minimum voltage is 4.5. So that should be good. The actual alkaline battery voltage is 1.6. It goes down to 1.5, so you'll probably be okay. Now if you use nickel metal hydride, you're going to need more batteries, because nickel metal hydride, nickel cadmium is typically 1.2 volts. So in that case, 2 of those would only give you 2.4. So that's not going to be enough. You may need another one. Another 2.4 would give you 3.6. So you need to, make sure that you look at your batteries very closely to make sure you're going to have enough voltage. Remember that batteries, they start off at a certain voltage and then they drop off very rapidly. So you may have, for an alkaline, you may have 1.6 and it may drop down to 1.5. So just remember that you're going to have, throughout the life of the battery, it's not going to be exactly constant. This is how a battery discharges over time. Now, because your battery is sometimes located remotely, it's not located directly close to your microprocessor, you have this problem of inductance. Again, the inductance is caused by the loop. You may have a battery here, and you may have wires going like this to your microprocessor. Again, twisting those wires together is going to eliminate this inductance, minimize inductance, but it's not going to completely eliminate it, but it will have a huge effect on the value of this inductor. You want this inductance value to be small. But if it's not, then you can also, another way to circumvent that inductance is decoupling. We call it decoupling the supply, and that's by putting a shunt capacitor across really close to the microprocessor. So if you were to have your microprocessor here, for example, these are your pins, say this is your supply, then we're going to want to have a capacitor really as close as possible to this, connected here on one side and then as short as possible. If possible, then you maybe could have it go under the board to there, or you maybe could have it on the back side of the board and just going across it to VSS and then VDD. It's really important to decouple that. It completely defeats the purpose to have your leads on your capacitor really long, because if you have your leads on your capacitor really long, say this is the capacitor, if you have these really long, well then the effect of, you're actually adding inductance. And remember, inductors and capacitors are opposites of each other, so they're corollaries of each other mathematically, so any sort of series inductance is going to cancel capacitance. So in that case, you're going to just null out the effect of your decoupling capacitor. Okay, so these are your decoupling capacitors. So let's look at an example. The example is the electronic ping pong game that's talked about in the book. Let's go through this example really quick and see how we're going to set up the hardware for this chip. Okay, so the first thing that we notice here is that we need to set up VDD and VSS. We need to set up our supply. So the way that we do this is we connect we connect a battery. There's going to be two different ways actually to power this. There's going to be through the PIC kit and through external batteries. Let's assume for right now that the PIC kit is not even here. Let's just assume that we don't have this connection over here. The PIC kit 3 is totally gone. So we're going to power this directly from the battery, but we're going to have a switch. So this would be your on-off switch. On-off. Okay. This would be your on-off switch. Now you're going to need to have a decoupling capacitor. Now this capacitor would act as your decoupling capacitor. Now even though on the schematic it's shown as being far away from the chip, that doesn't mean you put it far away from the chip when you actually do the layout. So when you actually do the layout, that capacitor, the 100 nanofarad, is going to be really close to the pin. Okay, so really a better way to draw it on the schematic would be to draw it right here. I like to draw things, you know, if the capacitor, I like to draw it really close to the pin just to kind of denote where it's going to be. Okay, so that's the first thing. Next thing is you need to have a ground, of course. So VSS is your ground. Before I move on to ground, let's talk about the PIC kit. Now, if it's going to be powered from the PIC kit, when you set up your PIC kit header, you're going to need to connect the VDD pin to your power. Okay, so you need to power up your PIC kit. Now, your PIC kit is very smart. It's going to, if you have the switch open, then it's going to supply power on its own. But if you have the switch closed, then it's not going to supply power. Now, the problem with this is if you power up your chip through your PIC kit with the switch open. Let's say that the switch is open. It's up in this up position. It's not connected, so it's open. If you power up your PIC kit and turn on your MP lab, it's going to detect to see if there's target power, and it's going to see if there's no target power, so it's going to power from the PIC kit. So it's going to put a voltage source here. Now what's going to happen if you flip the switch on? Well, now you're probably going to damage your PIC kit, and it's not going to be any good anymore. Because these two sources are probably going to be at slightly different voltage, and you're going to overload one of them. Okay? So you need to be careful. When you're operating off of your PIC kit, you need to let your PIC kit do all the work. Don't use your switch anymore. Don't use your on-off switch in this case. Your PIC kit's going to be supplying the voltage. Okay? Then if you disconnect your PIC kit, then it would be okay again to use the on-off switch. Then your VSS is just going to be grounded. Okay? So over here, if you're using battery, of course, you go off the negative terminal. Negative. This is the plus side of the battery. This is the minus side. You connect this to your ground, which really they use the wrong symbol. This is earth ground. Really the better symbol to use is this symbol. Or this is typically the chassis ground symbol. This represents a chassis ground, which could be accurate. But either symbol, this represents an earth ground. Okay? And then this type of a symbol represents an analog signal ground. So any one of these is fine, typically. Okay, so we talked about VDD, VSS. Of course, your PIC kit needs to go to ground as well. Okay, so next let's talk about your oscillator. How do we set up your oscillator? In this case, you can see that OS1 signal is going to a resistor and a capacitor. So it's a pretty good bet that they're using the RC oscillator inside of this design. So if they were using a crystal, then you would have a crystal here, and you would have two capacitors. You have two capacitors, and they would be configured like this. Okay, and this side here would go to ground. This side would go to ground. Okay, but in this case, we're not really doing that. So let's see if we can erase this really quick. We're not doing that. We're going to be using the RC oscillator. So this is the R, this is the C. You got a 10 picofarads and a 10K, 100 picofarads and a 10K. So the frequency is going to be 800 kilohertz nominal. Okay, so we got power, we got our oscillator. Now don't forget, inside the code, you're going to have to set up your configuration word. Okay, so don't forget about your config word. Config. You have to configure through your PIC kit, your MP lab. Your software is going to allow you to set that configuration word. It's basically going to be just this drop-down menu. You're going to click on this drop-down menu, options or something like that, and look around for a configuration word. We'll talk about that during the next chapter. Okay, so now we've got our clock set up. We've got our power set up. Now we need to look at our ports. Okay, let's set up our ports. So, how are we going to use in port A? This is port A, A0, 1, 2, 3, 4. So, notice that 3 and 4 is basically your buttons. That's your left and right button for your ping pong game. You get the left and the right. Now, port A, bit 2, is out of play LED. So, you have a current limiting resistor, and then you have your LED. Okay. Now, for port A, bit 1, we have the score A LED. Again, we have the current limiting resistor. You always have to have this, and you have your LED. So if you have a 2 volt, let's say you have a 2 volt LED, and maybe you have this is a 5 volt part, so you have 5 volts here. You'd have 3 volts across this resistor, and then you're going to have your I is going to be 3 volts then over the R value, which is 560 ohms. So that's going to set your I. So remember, your I, the more current you have, the more I there, which is your current, the more you're going to deplete your battery. So your battery life is going to suffer. So you want to have this number as little as possible. So in other words, you may want to increase the value of this R. That would be my recommendation. To try to make the R as big as possible, but then as you start to increase it, then you're not going to be able to see your LEDs anymore. So there's a sweet spot in the middle where you're going to have to adjust it. And this is just kind of trial and error type thing. Or you can look on the LED data sheet and see, you know, what is the recommended nominal value for the current. You know, maybe it's 1 milliamp, maybe it's 10. Okay, so we got the port A set up. We're using the port A for the left-right paddle buttons, and then we're using it for the score lights, and then the out of play. Now note that the left and right buttons are going to be configured. You have to configure these two bits, bit 3 and 4, as inputs, whereas bit 2, 1, and 0 need to be configured as outputs. Okay. So now let's look at. We forgot to do our clear. This is your master clear. Now note that your master clear in this case, let's assume we don't have the PIC kit, then we need to pull up the master clear with a pull-up resistor. Okay? So we're going to pull up the master clear, because the master clear is actually inverting logic. It's master clear not. So it has a slash over the top of it, which means it is active. The clear is active low. Now if you wanted to, with this pull-up resistor, you could put a switch, if you wanted to have a switch here, to ground, and then when you would push the switch, then it would reset your microprocessor. So that would be optional. Now, if you're using the PIC kit, now you need to wire this clear, which you're definitely going to be using the PIC kit, so you need to also wire this clear to the PIC kit master clear as well, which is called VPP/master clear. That way, when you go to program your part for the first time, you connect this PIC kit into the header, and then you program it. Now you have to configure your board, remember, to work with the PIC kit and without it, because you need the PIC kit to work when you program the chip. The only way to get your software inside the chip is to connect the PIC kit. Now when you're done programming it, you take it away, and when it goes out into the field or it goes into the actual device, you're not going to have your PIC kit here. So you have to wire up your diagram where it works with both the PIC kit and without it. Okay, so remember that when you're designing your board. It has to work with it and without it. Now, so we have the master clear. Notice that for the paddles, for the push button switches, we also had to have the pull-up resistors. Okay, now we talked about that a little bit as well. So the pull-up resistors are needed because when you push the switch, it's going to pull down to ground, because this side is pulled down to ground. Then when you release the switch and put it in the up position, then it's going to pull these pins high. If you didn't have the resistor there, when you push the switch, you would have infinite current flowing through this, ideally infinite current, and it would completely deplete your battery. Your battery would be dead in a matter of seconds. Okay, so you have to have these resistors here. Otherwise your battery is going to be dead. And again, you want these as big as possible, as large as possible to minimize the amount of current through them. The final thing we need is we need our ball flight LEDs, which is going to be 8 of them. We have 8 of those, so we're going to use port B, bit 0, 1, 2, 3, 4, 5, 6, and 7. And then again we have the current limiting resistor, and then we have the LED. Now the final thing we need to set up is we need to be able to get our software code, our assembly file, .asm file, which we will talk about next chapter. We need to get our assembly language file into the inside of our chip. Now the way we do that is we have a programming clock and then we have a programming data pin. That just happens on the PIC16 LF84A. It just happens to be on port B7 and 6, so it's a multifunction pin. So we connect the data here. We go up here and we connect it to data, okay? And then for the clock, now if you look on your data sheet, you can see these. You connect it to your clock. Now, when you go to program your chip with MP Lab, then your data and your clock are going to toggle on this line, and it's going to configure your chip. Now, once it's configured, it's going to be remembered because it's going to be programmed into flash, okay, which is non-volatile memory, so it's going to remember it. Now you can take your PIC kit away, you can eliminate the PIC kit, and now it's going to be remembered inside here. And you also have, now you have power, you have everything that you need. The chip has the software inside of it, it has power, it has the master, it has the clear, the reset is going high, so it has everything you need. It has an oscillator, so this chip is completely configured the way it needs to be. So thank you. We're done with chapter 3, and we talked about a little bit of the theory, how to set it up, and then we talked about this practical application of the ping pong game. And if you look in the book, in the appendix, I believe it's appendix 2, then you can see, yes, it's appendix 2, you'll see the schematic for the ping pong, which we just went over. You also see the assembly language code that you can look at as well. You have a complete system. And if you go on the supporting website, then you can download that assembly language code and use it as an example. Thank you very much.